Good afternoon, everyone. So today I'm just really pleased to be here in front of you to talk about something that's probably on every one of your minds. What on earth is going on? 2023 has seen some of the largest climate, weather, and ocean extremes in recorded history, going back centuries to even millennia. So what does this mean? What's causing it? What can we do about it? My name is Peter de Menocal. I am the 11th president and director of the Woods Hole Oceanographic Institution located in Woods Hole, Massachusetts on Cape Cod, right about here. The Woods Hole Oceanographic is the world's leading oceanographic institution, independent oceanographic institution, and we specialize in ocean science, ocean technology, operate ocean vessels. Now, I joined this program about 3 years ago. Before that, I had one employer. I was at Columbia University for 33 years. I received my PhD there in geology and geochemistry and oceanography. And my last post there was actually Dean of Science, so I made my way up through the mailroom. But I took this job, I left tenure to take the leadership of the Woods Hole Oceanographic for a simple reason, and it's really the takeaway point for today, which is that the ocean is the single biggest cog of the planet Earth. It regulates our climate, it determines our habitability of the planet. And we're going to walk through this today. So what happened in 2023? What is happening in 2023? Some of you will remember this image of New York City. I was actually in Washington, D.C. at the time when these Canadian wildfires, the smoke from the Canadian wildfires, really enveloped the East Coast. These smoke records from Canada, the burned area, smashed records. There's more than twice as much burning occurred this year than any time in the past. And a big part of our understanding of this is what's causing this. When we actually look at some of the other climate extremes of this year, they include this record 31-day unbroken stretch of over 110 degrees Fahrenheit in Phoenix, the most extreme heat wave they've had. Some of you are from South Florida, where they had ocean temperatures in excess of 101.1 degree Fahrenheit. That's the warmest ocean temperature ever measured anywhere in an open ocean setting. Something very weird is taking place in Antarctica right now, and we're going to review that in a moment. And for those of you who know burners or were actually just returning from Burning Man, there were 70,000 people who were stranded on Burning Man or were stranded in the desert because of this torrential downpour of rainfall, which is very unusual for that region. So we're going to be asking ourselves, what makes an event extreme? What makes an event extreme is that it's outside the bounds of what's normal. What makes something normal? What makes something normal is whether it's outside the bounds of variation or the standard deviations. So plus or minus 2 standard deviations away from the average captures about 98% of a population. I know I'm about to lose all of you right now, so I'm going to stop there. That's the last of our intro of statistics. What we're concerned about are those extremes on either end. This is what makes an event extreme. So some of the things that we know that have a distribution like this are height, the size of your shoe, your intelligence. Another one that I'm going to make a little bit more personal is life expectancy. Life expectancy is approximately normally distributed. And just to give you an idea, the average life expectancy in the United States in 2019 was about 78 years, with a standard deviation of about 14 years. So if you lived until 78, you had the average lifespan of an American in 2019. So shown here on your right are my parents. My parents were married for 70 years, and the year I took this job at the Woods Hole Oceanographic, they both passed away within about 2 or 3 months of each other. They died at a good age. They had been married 70 years, and they died at 93 years old. So that's plus 1 standard deviation. The middle panel actually shows my aunt, Bab Simpson. She died at the age of 105, actually, around the same time. That's plus 2 standard deviations. So I'm not bragging about the longevity of my family line here. But when we look at the oldest person that's ever lived that's been verified, it's Jean Calmet. who's here, shown here on the far left. And Jean Calmet died at the age of 122, the oldest person ever recorded in history, and that's plus 3 standard deviations. So if you met somebody who was 140, 150 years old, that would be really extreme. So this is the context by which we can begin to understand what's happening in terms of global climate and changes in ocean and weather properties around the planet. This month, actually July, the month of July, was the warmest planetary temperature, air temperature, ever measured in recorded history. That means that when we take the average temperature of the planet using reliable thermometers, average them all up for the planet, last July was the warmest month ever measured. More than that, actually August broke that record. So last month in August actually was the warmest month ever recorded. 2 record-breaking months in a row. Those are 4 standard deviations above the mean. That's one way to describe extreme weather. If that was a person, they'd be 142 years old. So now we turn our attention to the ocean. Now, the ocean is interesting because it has a heat capacity, water has a heat capacity that's 3,000 times that of air. So when the ocean warms, it really means something. So here's a video clip from a fellow colleague of mine who was at Columbia University, who is now running a weather channel in Florida. This is a video he has. What's shown here is in red are the temperature extremes for the ocean in July. In the North Pacific, 7 degrees Fahrenheit warmer than usual. In the Eastern Pacific, 9 degrees Fahrenheit warmer than usual. The North Atlantic is the warmest ever measured. And then there's this little data point for Florida. This is right around when they had that 100-degree temperature. And then right off the waters here off of New England, it's 14 degrees Fahrenheit warmer than usual. The whole planet is on fire. That was also 4 standard deviations above the mean. So now we turn our attention to the other part of the planet, Antarctica, and we look at the sea ice extent around Antarctica. The normal range for the sea ice extent is shown in this yellow line that's showing the median extent. That's where it normally is over a 30-year period between 1981 and 2010. And you can see where it is today, shown there in white. It's much less than that. In fact, it's less area. It's equivalent to the size of Greenland. So it's a huge amount of missing ice. That is a 6 standard deviation departure, which is equivalent to meeting somebody who's 162 years old. So why is this happening? I think the important thing to think about is within the kind of larger context of what's going on. Of course, we're building up greenhouse gases in the atmosphere. That's obviously contributing to this to some extent. Let's break it down. Let's break it down into the relative components of what's causing the warming, because there are natural factors like volcanoes going off and El Nino variations. There's also human-caused factors like greenhouse gas emissions and deforestation and changes in aerosols in the atmosphere. So let's look at all of these things one by one. So in black is the instrumental record of temperature change for the whole Earth going from 1880 up until the present, about 2015. And what we're going to do is look at how much of this warming is due to different factors. This is work that was published by a colleague of mine at Columbia, Dr. Kate Marvel, published in Bloomberg. What's really fascinating is we can start to see how it all comes together. In this blue line that's shown here is variations in the Earth's orbit around the sun that caused the ice ages. You can see it had really no impact. Changes in the sun's luminosity over this time period, almost no effect. Changes in volcanic eruptions. Well, you can see it does cause some cooling events that you actually see in the instrumental record. It's a good fit, but you're not capturing that warming. So now let's look at the human-caused factors. We can look at changes in land use, such as cutting down the rainforests, or changes in the ozone concentration, has a slight warming effect. We can also look at changes in aerosols. These are things that block out the sun and cause it to cool. If we look at greenhouse gases by themselves, it's too much warming relative to what we observe. Now, if you add all the human-caused factors together, you get some that go up, some that go down, but you average them all together, and you get a pretty good fit. But the trick comes when you add the natural factors and the human cause factors together, everything that we know that can impact climate, and you get a perfect fit. That's how we know that the majority of the warming is due to greenhouse gas emissions. The other thing about this year, 2023, that's unusual is that there's a really big El Nino that's developing right now. El Nino is a natural sloshing of water in the equatorial tropical Pacific. Some years it's colder than average off of Peru, some years it's warmer than average. When it's warmer than average, like this year, that big red blob that's roughly twice the size of the United States, that's called an El Nino. We know that El Nino years cause there to be unusual warming for the whole planet, so that's certainly part of the puzzle for this year, what makes it so extreme. So now I'm going to show you some new results. And one of the really great things about what I can show you today is that these are new results. Very few people have seen these. And this is a way for us to understand what's happening this year with respect to comparing all the years in the past. This was work conducted by a colleague of mine, Dr. Zeke Housefather. And this is results that were just published about a month ago, or in fact, they were just presented publicly a month ago. They're not yet even published. And this is using what's called a digital twin of the planet. This is a computer model, very complex computer model of the ocean and the atmosphere that looks at how all that natural and man-made forcing will impact the ocean temperatures on the planet. Looks at all the possible scenarios, a La Nina year, El Nino year, warming, cooling. And you can see it forms an envelope. That is this 2 standard deviation envelope. If you plot where we are for July in 2023, or even for August, you'll see it's within that range. So what we're seeing today is actually, surprisingly, exactly what we expect. Where it becomes kind of interesting is when we start asking the question, well, what happens if we look at 7 years into the future, just less than a decade, 2030? What we're experiencing this year becomes average. It's the thing that we expect. It's not the extreme. Perhaps even more amazingly is that when we go to 2050, so roughly 25, 27 years from now, today is the coolest of all the possible outcomes in this model, assuming carbon emissions continue as they're going up today, and that's part of the clue. What's additionally kind of mind-blowing is that actually if you go out to 2100, the year 2100, this year doesn't exist in the future. All possible years are warmer than today. So whatever extremes we're seeing this year, they're nothing compared to what we'll see at the end of the century. So now, I know you're all running for the doors. And the point is to really focus on how we're going to fix this. It does us no good to take a doomer stance. It does us every bit of good to think, how can we use our minds, our ability to shape our futures to fix this problem? And that's why I'm here today. So there are 2 steps to fixing climate. It is that easy. There are 2 big steps, but there are 2 steps. The first is reducing carbon emissions by 90% within the coming decades. It sounds like a tall order, but I'm happy to say we're already on our way to doing so. So the first most important job is to stop emitting, putting it in the atmosphere. The second part, and this is again a new result that we've landed on in just the last year or so, is that that's not enough. We actually have to now pull carbon dioxide from the atmosphere, remove our legacy emissions. It's not going to offset the emissions we're putting in today, but it will take up old emissions, which is what we have to do to keep the Earth below future warming levels. So let's break this down a little bit. There's a project called Project Drawdown that has published a really wonderful series of steps that we can take to achieve this 90% reduction in emissions. And I urge you all to visit this site, projectdrawdown.org. On this is a list of over a dozen or so actual, doable, actionable, functioning, scientifically proven approaches that will work. So one of them is deploying offshore wind turbines. That's the one at the top. The second one is utility scale solar. Those are 2 things that you all know about, things that we should be doing at scale right now. The good news is that we're already bending the curve. That is, from Economics 101, you learn that Wealthy nations have high emissions, less wealthy nations have low emissions, and it forms a perfect line when you look at all the nations together. What is happening in your lifetime, what has happened in your lifetime, is that we're bending the curve. We are decoupling the wealth, which is increasing upwards. So the United States has doubled its wealth since 1990, and we're actually emitting less than we did in 1990. The United Kingdom is even doing this more so. Most of the Western European countries are doing this even to a much higher degree. So we're starting to bend the curve on emissions while maintaining wealth. So step 2, the second step is to remove carbon dioxide from the atmosphere. And it is as hard as it sounds. Carbon dioxide removal is like a way-back time machine. It's a way to send us back into a time of lower carbon dioxide concentrations in the atmosphere. Now, it sounds difficult, and it is. This is a facility developed by Climeworks that's in Iceland, and it is literally a vacuum cleaner for carbon dioxide. Those big vents on the side actually draw in carbon dioxide, capture it, they liquefy it, and pump it underground for durable long-term storage. This is great. We need to do more of this. This facility takes up about 4,000 tons per year. Now, I know that sounds like a lot, but in order to appreciate these numbers, because the numbers get big and it's very hard for people, myself included, to kind of make sense of it. So we can scale it to today's emission rates, how much emissions we emit to the atmosphere every day of CO2, and that's about 40 billion tons a year. Now, that's an impossible number to get your head around. So let's think about it. This plant in Iceland, this facility in Iceland, how much carbon is it taking up each year? It's about 3 seconds. It's a good thing to do. We need more of it, but it's just not going to scale. And this is one of the reasons why I'm so pleased to speak with you today, because we're all about scaling. Now, another approach that I think all of you have heard about is growing trees. Why don't we grow gazillions of trees? There are lots of proposals out there to plant 100 million trees or 1 billion trees. So if we planted 100 million trees, that's roughly, it's a small national forest worth of trees, perhaps. It's a pretty big deal. If you actually work out how much carbon removal this represents per year, assuming it doesn't burn down, it's about a half an hour. So it quickly becomes apparent to everyone in the room that it's hard to scale these terrestrial processes, in part because it's only about 29% of the planet. We're going to need a bigger boat. And that's why I'm here to talk to you as the director of the Woods Hole Oceanographic Institution. When we look at the ocean, just like today, for all the people who are in the room, right now you're metabolizing your lunch. You're all breathing, and you're inhaling, and you're exhaling carbon dioxide. This room has been steadily increasing in carbon dioxide concentration. So imagine that each of you is a factory, and you're emitting into this room. This glass of water here, if any of you have a glass of water, the chemistry of that glass of water has changed in just the time I've been here on stage. It's become more acidic because the carbon dioxide from the atmosphere is equilibrating with the water that's in that glass. And this is exactly what the ocean is doing, but the ocean is 71% of the surface area of the planet. So the ocean is doing us a huge solid right now by taking up a quarter of our emissions every year. 25% of our emissions every year is taken up by the surface of the ocean through what's called the solubility pump. Now, how much is that worth in terms of time? Well, you can sort of do it in your head. It's not hard to do. It's about 3 months, a little over 3 months. So the ocean, without us asking it to do anything, is already by far the biggest buffer on climate change that we have. It takes up also 93% of the excess heating from global warming. So the ocean is a climate hero, and that's one of the really big takeaways from today. More than that, because the ocean's also a living medium and all that organic matter also accumulates in the average 4 kilometers depth of the ocean is a vast carbon reservoir. It's actually 50 times greater than the atmosphere. So it's the biggest exchangeable carbon reservoir on the planet. And just to give you an idea of how big it is, if we could take all of the carbon dioxide that's in the atmosphere today, that excess that we put in there since the Industrial Revolution, if we could ball it all up and mix it into the ocean like a martini, every ocean top to bottom, it would represent about a 1% addition to the carbon reservoir of the ocean. The ocean has done this many times in the geologic past. It's a natural phenomenon, it happens. What we don't know is how to do it in a deliberate way, and whether it's safe, and whether it's effective, and whether it's durable. And that's where we're going now. The National Academies of Science, the premier organization looking at the state-of-the-art science, has looked into what are the ways in which the ocean can be induced or enhanced carbon uptake. This includes nutrient fertilization. One's called alkalinity enhancement, which is making the ocean slightly higher pH or more alkaline. And another way is the easiest one to understand: grow a lot of seaweed, bale it up, and sink it to the bottom of the ocean like a leaf pile. Now, these are all scalable approaches. We know they work, but they've never been tested to see whether, A, they work at scale, B, whether it's safe, and C, whether it's durable, whether it's lasting storage. But the ocean can do this at gigaton scale. We know that for a fact, and it's the only thing that's available to us that's at that scale. So what can we do? So venture funds are flowing into what are called MCDR, or marine carbon dioxide removal startups and technologies. They're doing so because all of them realize that the ocean is the biggest player in the climate solutions field. The ocean is the 800-pound gorilla. This is one example of a startup called Captura that was developed by a group of Caltech professors, and it was looking at using renewable energy from solar panels to drive electrolytic chemistry changes in the ocean to take up more carbon dioxide. It just requires sun, it requires seawater, and you can take up carbon dioxide. Recognizing this opportunity and just recognizing the dearth of investment vehicles to drive this technology development, I had a chance encounter with our hero and co-founder of HubSpot, Brian Halligan, sitting right here in the front. And, and we had a lunch meeting at a small restaurant in Falmouth, which is right next to Woods Hole, where we sketched on a napkin some of the technologies, some of the ideas, and we worked through some of the numbers. It goes, this is fantastic. How come we're not doing this? And I said, well, we need this catalytic capital to drive scientists and engineers to do this work. He goes, what's the number? And I told him, he goes, that's a big number. And so we went right to the top and said, how would we do this? And after about a year and a half, we arrived at a venture fund called Propeller. Propeller is designed to invest in startups and technology development to drive these ocean-based climate solutions that we're going to be talking about in a moment. Together with Deb Yellerkar, the two founders with Brian Halligan, we developed Propeller to be this agent of change, to be this lever to drive the kind of change we're talking about. So these marine carbon dioxide removal startups are growing fast. There's dozens upon dozens that focus on seaweed cultivation, enhanced weathering, this alkalinity enhancement that we talked about earlier, this electrochemical work that I showed you, that early facility from Captura. They're growing fast. In fact, carbon removal market increased last year by 500%. So the market, the appetite for these kinds of solutions is huge. So how can we scale up to meet that? The challenge, the thing that's holding us back, is our ability to observe these carbon changes in the ocean. If we ask ourselves, how can we take the temperature of the ocean? That's easy, we do that. We have 4,000 robots. The Woods Hole Oceanographic is the leader of one group of these. We have 4,000 robots that are literally just pogo sticking up and down the ocean. They go down a half a mile, they go up to the surface, they make measurements of temperature and salinity throughout the way. That's how we know the oceans are warming. They phone home, send their data, purge their buffers, go back down, make more measurements. 4,000 of these in the oceans. We got the ocean covered in terms of temperature and salinity. But when we ask how many of these things can actually measure the carbon system, this very thing that we have to measure to determine whether marine CDR will work, we're flying blind. We have really no eyes on the ocean carbon system for 71% of the planet and all the way down to the bottom of the ocean. We've got nothing. Very, very few measurements. And this is the focus of a new initiative at the Woods Hole Oceanographic that's actually engaging partners, institutions nationwide and indeed around the world. We are building the world's first ocean internet. So if you envision an upside-down Starlink, that's what we're building. This is an always-on, always-connected ocean internet of sensors focusing on ocean health and ocean carbon to inform the ocean's ability to take up carbon, the status of ocean health, and our ability to measure, monitor, and verify these carbon flows. So this involves a lot of technologies that actually we can do today, right now. So one of them is, for example, we can send a vehicle out on a 2-week mission, and it can navigate itself into a tube that's only 8 inches greater in diameter than the vehicle. When it does that, it can download its data using optics and using blue lasers, actually, and using acoustics. It can also go down and repower and draw power from wind and solar energy on the buoys. We can also do connections to satellite from buoys. And we can also do machine learning and AI for intelligent swarming of vehicles, so they can tell each other intelligently how to sample the ocean. All of this stitched together is what we're calling the Ocean Vital Signs Network. The Ocean Vital Signs Network is this constellation of sensors in the ocean that are monitoring ocean health, ocean carbon uptake, so that we can evaluate these marine carbon dioxide removal technologies, but mainly monitor an ocean in transition, because we fully depend on the ocean every day. Every breath of oxygen, or rather every other breath of oxygen, comes from the ocean. So if you imagine we have this network, what does it allow us to do? Well, if we have a flow of carbon, let's say on the left-hand side is what's called the classic biologic pump, how the ocean normally works. Algae grow in the sunlit part and ray down to the deep sea. If we had an enhanced carbon removal technology where you're sending more carbon to the deep ocean, where it can be stored for centuries to millennia, the way to monitor that, the way to measure that, is through this Ocean Vital Signs Network. We are beginning this work this year. So if there was one takeaway for today, I would ask you to remember that climate solutions, and we have to have solutions, climate solutions are going to be ocean solutions because we are an ocean planet. 2023 is extreme, it feels extreme, but it actually isn't. It's exactly what we expect. And we look into the future, it's something we get a sense of what the future might look like based on what it looked like this year. It's important to take home that there are actionable solutions. We know what to do, and we can do that work right now. In fact, we're doing that work right now. And last is that the ocean is the climate hero. Thank you.